Okay, so now we will talk about the conservation law of momentum, which actually is a very, very important principle on physics. And when you see in your data booklet the physics principles sorted, the conservation law of momentum is part of those principles. Now, remember what we said, recall what we said on the part one of the video series of the conservation of momentum and impulse, that we have um, three types of system. It's the closed system, it's the open system, and it's the isolated system. And when we talked about the closed system, no mass enters or leaves the system. An isolated system, no external forces act on the system, and no energy leaves or enters into the system. And the open system, mass and energy may enter or leave the system. The conservation law of momentum is saying that total momentum of an isolated system remains constant. So in an isolated, this is the law. In an isolated system, the momentum of the system is constant. Is constant. So keep in mind what we said. In isolated system, no mass nor energy is entering or leaving the system. And when we are talking, the momentum of the system is momentum of all the parts or all the objects that the system has. So in other words, what it is saying that the total momentum of the objects remains constant before and after. Or in other words, the momentum of each part of the system may change, but the vectorial sum of momentum of each part of the system before and after remains constant. This is expressed on this formula. The sum, this sign here means the sum of momentum of the objects before is equal to the sum of momentum of the objects after. This apostrophe sign here indicates that you are calculating the momentum of the system or the objects after the collision or explosion. Actually, the conservation law of momentum is a direct consequence of Newton's third law and Newton's second law of motion. So recall here what we said in terms of the third law. Every action has an opposite and opposite reaction, so same magnitude and opposite sign. And then what do we have here is that on the other hand, force. So if we have this force that object one is exerting on object two is the same as the force that object two is exerting on object one. And then from here, what do we have is that the force is, if we consider it as force net, will be mass of object one times change of velocity that object one is undergoing, 2 over the time that this change is happening is negative to mass 2 change of the velocity that object 2 is undergoing, 2 over the time that the collision or the change is happening. And if you cancel out those times, because it is the collision is happening at the same time, you cannot have collision between two objects that it is happening it is happening in two different times. They are in contact between each other into the same time, M2, negative M2 delta V2. And if you add M2 delta V2 in both sides, then you will have that M1 delta V1 plus M2 delta V2 is equal to 0. So this is telling you that the total change of momentum of a system is 0, and this is also known as the conservation of momentum. Now, when the two objects are collided between each other, what is happening is that it is something like this. Object 1 with a given mass 1 and a velocity v1 is colliding object 2 with mass 2 and let's say velocity 2. And this is what is before the collision. And then during collision, what is happening? Object 1 and object 2 are in contact between each other for a certain time, delta t. So this is during. And what is happening after the collision? You have object 1 and object 2. Let's say that mass still mass 1 and mass 2 that are moving with after velocity, the velocity after the collision v prime 1 and v2 prime, like this. Okay, so this is after the collision. The object of physics 30 is what is the conservation law of momentum, what is the velocity right after the collision. So we don't deal too much with what is happening 3 seconds after the collision have happened. Okay, so now when we are working with collisions, like in everything that it's new to you, what we do is we classify the collisions. And the collisions are classified in 3 types. So types of collisions. The first one is elastic collision. So what is happening during elastic collision? Both momentum and kinetic energy of the system is conserved. During that second type, which is known as the inelastic collision, momentum is conserved, but kinetic energy of the system is not conserved. And the third type of collision, which is pretty much under the inelastic, but it is taking the power to be called a separate type of collision, is explosion. And during this type of collision, momentum is conserved, but kinetic energy of the system is always increased. It's going from 0, because you are at rest in most of the cases, into explosion of 2 or more pieces. So sometimes some textbooks call it as a unique case of inelastic type of collision, and in some cases it is just its own type. Okay, so what we are talking here is always an isolated system, because in an isolated system, momentum is conserved. Okay, if momentum is not conserved, then we are dealing with a non-isolated system. Okay, because the momentum is not conserved. So when you have a question that momentum before and momentum after is given, and you are comparing, the system is given, and you are comparing what is the, are they equal or not, then what you are doing is you are classifying the system of the objects that you are dealing with. And if it is conserved, momentum before and momentum after, then the system is isolated. If it is not conserved, then you should say that the system is non-isolated system. Okay, so now all the type of collisions again that we are talking here, we are dealing with a system that is an isolated system. Let's see now some examples in which we are classifying the type of collisions. So let's suppose that we have an object with mass 1 of 2.50 kilograms and a velocity 1 at going in the positive direction. So let's say that it will just do it as a 1D for now. So going in the positive direction with a magnitude of 5.20 meters per second. And then you have the second object, object 2, with mass of 5.20 kilogram with a velocity 2 of a negative 3.80 meters per second. They collide, and then what do we know? So this is before. And then after the collision, what do we know is we are looking for the velocity of object 1 after the collision, knowing that the velocity of object 2 after the collision is, let's say, positive 1.10 meters per second. So this is the after situation, after the collision situation. So now what do? Is we start with writing, assuming that this is an isolated system, we will write the conservation law of momentum. Conservation law of momentum is stating that momentum of the system before is equal to momentum of the system after. In this case, what do we have? We have 2 objects in our system. So this is saying that momentum of object 1 before plus momentum of object 2 before is equal to momentum of object 1 after plus momentum of object 2 after the collision. What do we know in terms of momentum is that it is mass times velocity for object 1, mass times velocity for object 2 equals to mass times velocity after the collision plus mass times velocity of object 2 after the collision. In this relationship, what do we know is we know everything but velocity of object 1 after the collision. Let's plot the information that we have. So mass 1, 2.50 and 5, positive 5.20. So 2.50 times positive 5.20 plus mass of object 2 is 5.20 and negative 3.80. So 5.20 times negative 3.80 is equal to mass of object 1 is 2.50 times velocity of object 1 after the collision plus 5.20 times the velocity of object 2 after the collision is positive 1.10. This now turns to be an equation with one variable, that is vi prime. Let's solve this using the calculator. So those are the steps that you should do, and this is what you should find as the velocity of object 1 after the collision. So this is telling you that the situation is very similar to the situation that we drew before, where we have the two objects that are going towards each other, and then they are collided and then moving in the opposite directions. Now the question will be, what type of collision is this? Is elastic, inelastic, or explosion? So let's see now if the conservation of energy is conserved before or in comparison to the after the collision. So the sum of kinetic energy of the objects, is it equal to the sum of kinetic energy of the objects after the collision? In other words, kinetic energy is 1 over 2 mass of object 1 V1 squared plus 1 over 2 mass of object 2 V2 squared. Is it equal to 1 over 2 mass of object 1 V1 prime squared, the one that we just found, plus 1 over 2 mass of object 2 V2 prime squared? So the information that we have in terms of mass 1 and mass 2, V1, V2, and V1 prime, V2 prime. Some of them we found, and some of them the problem is giving us. And then now let's check if the conservation of energy of the system before the collision is the same as the conservation of energy of the system after the collision. If it is conserved, then we can say that we are dealing with an elastic collision. And if it is not conserved, then we can say that we are dealing with a completely inelastic or inelastic collision. So stop the video and do the calculations. You will see and compare your calculations with mine. So this is the work that it's done in terms of calculating the kinetic energy of the system before, and then you will have the kinetic energy of the system before, which is the sum of the two kinetic energy of the two objects. Keep in mind, kinetic energy, like any energy, is equal to the it's a scalar quantity, and the units are in joules. If you want, I can refer to you to a video in terms of the how to calculate kinetic energy. And the two sides, before and after, are not equal to each other, and since they are not equal, the collision is completely inelastic because the two objects are moving away from each other, but it is happening in an isolated system. Let's take a look now to another example where one of the object is at rest. So let's suppose that we have an object 1 that is with mass of, I don't know, 40 kilograms, and an object that is at rest. Rest means is equal to 0. And then you have an object 2 with mass of 30 kilograms that is moving with a velocity that is going in the west direction of, let's say, 52 meters per second in the west direction. And then what is happening after that? The two objects are stick together and they move, see, like a together, and they move as one object. What is the velocity of the object 1 and 2 as they stick together? Okay, so velocity after the collision and the two objects are stick together. So again, we are assuming that we are dealing with an isolated system. So in this case, the conservation law of momentum is saying that momentum before is equal to the sum of momentum after. Momentum before is equal to the sum of momentum after. And we are dealing with two objects, so we'll have momentum of object 1 plus momentum of object 2 before the collision is equal to momentum of object 1 plus momentum of object 2 after the collision. Now momentum is mass times velocity, so this will be m1 v1 plus m2 v2 is equal to m1 v. Now, since the two objects are stick together, then momentum of those two objects will be just momentum of object 1 and 2 stick together. Okay, so in this case, what we will have will be mass 1 plus mass 2. So because we have two objects that are sticking together, mass 1 plus mass 2 times a velocity after of object 1 and 2 stick together. So since the object 1 is at rest, then the whole thing here will be 0. Then we will have mass 2, velocity 2 is equal to the sum of the masses, mass 1 and mass 2, since they are sticking together, velocity 1 plus 2 prime. On this equation, we know everything but the velocity, so let's plot it down, and then we will have going west, we can say that is negative, so 30 plus times 52, 30, that is the mass, times negative 30, 52, is equal to 40, that is the mass of object 1, plus 30 times v1 plus 2 prime. And then from here, using math, we will find that the velocity of the two objects after the collision will be negative 22.3 meters per second, or you can say it's 22.3 meters per second going in the west direction. So now the third type of collision that we will see is the explosion. And what is during the explosion is that what do we have to keep in mind is that the kinetic energy and as well momentum of the piece before the explosion is equal to 0. And then after the explosion, some will be given and one thing will be that we will find out. But what we will do is we will use the fact that the conservation law of momentum is applicable. And during explosion, always the kinetic energy, as we have said, is even on the first part of this video series, is increased because the initial one is equal to 0. So let's see an example where, let's suppose that a rifle with mass of 4.7 kilogram is firing a bullet that has a mass of the rifle and mass of the bullet with 0.012 kilogram. The bullets are way smaller than the mass of the rifle. And then the velocity of the bullet is 380 meters per second going in the east direction. Now, what is the recoil velocity of the rifle? Okay, so this is after the rifle after. Now, if we draw the situational diagram, then we will have a rifle that is here with the bullet on it, and the mass of the rifle and the mass of the bullet will be 4.7 plus 0.012, and then using the calculator we can find that it is 12 is 4.712 kilogram as the mass of the rifle and the mass of the bullet. So now this is the before situation, and after, what is happening is the rifle that now is without the bullet will be having a velocity that goes like this, which we don't know and we will find, while the bullet is having a velocity of 380 meters per second going east. So let's start with the conservation law of momentum. Momentum before of the system is equal to momentum after. Now, before we had the mass of the rifle and the bullet, but they are at rest. And then after that, we have two parts now. We have the bullet that is having a certain velocity and the rifle that is having another velocity after the collision. Now, since it is at rest, then the whole thing here on the left side of the equation will be equals to 0. And then we have the mass of the bullet as 0.012 times 380. And it is positive because it is going east, plus 4.7, that is the mass of the rifle, times the velocity of the rifle after. And from here, we find that the velocity of the rifle after the collision will be negative. It is 380 times 0.012 divided by 4.7. And it is negative 0.97 meters per second. You can say this as a negative, or you can say 0.97 meters per second going in the west direction. Okay, so this is a collision in one direction. For the next following video, what we will see is how can we deal with collision and classify the collision when we have 2D situation. I will see you on the other video.